Alright, so the first serious application we'd like to talk about of electromagnetic effects is called an AC generator. I've got a couple pictures here of actual AC generators. This one would run on gasoline or possibly diesel, and that's one that could power your house perhaps. Maybe some of you even have a generator that you could use if power is lost. You could turn on your generator and provide power for your house. This is a much, much larger generator that would be located at a power plant. You can see for scale there's a gentleman standing next to it. It's very large. This one for scale probably would come up to your knees maybe if you were standing here. So this is what they look like on the outside, but of course we're interested in what they look like on the inside. So this video will probably be pretty short, but let's go ahead and talk about details. Alright, so this is a diagram form of what an AC generator might look like. This is non-diagram form. It might look something like this. This is probably actually an AC motor, but as we'll talk, as we get more into this, you'll grasp that the same exact setup could act either as a motor or a generator, depending on what you do with it. In any case, the very basic diagram, let's zoom in on that diagram form. No actual AC generator looks exactly like this, but it makes it easier to see what's happening. So you might have basically some device that you're using, which we would call a load, hooked into a circuit here. And then these brushes would be basically like loose wire or sort of like if you think of maybe like a steel brush. If you think of a steel brush that you've seen before, take part of that steel wire brush and you would hook it up to a circuit and then have it touching what's called a slip ring. So this is a solid metal ring which would be attached to some kind of usually an axle that would go through here. And then this ring would be attached to the axle, and this ring would also be attached to the axle. So the axle is not shown in this diagram. So you have two slip rings. One slip ring attaches to one end of this loop of wire, so that would be this one coming through here attaches to this slip ring. It does not touch this slip ring, so this wire goes through here and it's only attached electrically to this one. So both ends are attached to slip rings. This end is attached here, and you follow it around, that end is attached there. And then each slip ring is hooked into a circuit that's going to use the electricity that we produce. So basically you would need something attached to this loop of wire that will spin it. In this case we're spinning it this direction, clockwise, inside this magnetic field. South pole on this end, north pole on this end. So basically if you spin this wire in there, you're going to generate an EMF, a voltage, a current that's going to flow through this complete circuit. Okay? That's the idea. You have to have some kind of mechanical device that is actually going to physically spin this loop of wire. Right? If you had you could do it with a handle, but that would be extremely inefficient. Usually they have turbines or basically giant fans that spin to cause these things to spin. In any case, what you need is something mechanical that will cause that loop to rotate, and that's going to produce your alternating current. Now, once it's produced, and again, you don't just use one loop of wire, you would use a bunch of loops of wire, which is the main thing I want you to see in this diagram here. There's lots of wiring going on. You don't just use one loop of wire, but it's easier to see what's going on with the one loop of wire diagram. Now, the voltage output of spinning that loop of wire in that magnetic field is shown here. When the wire is in the vertical position, actually I'll show this again on the next slide with pictures. So we'll just go over it really quick. Basically with alternating current generator, you're going to get a sine wave of voltage. Alright, sometimes you're at 0 and sometimes you're at a peak positive, and sometimes you're at a peak negative, right, or a trough, if you will. So high positive current, high negative current, and back to zero. So you just oscillate. Alternating current oscillates between a maximum positive and a maximum negative value. All right, and we just want to talk about which positions of the loop correspond to which positions on the graph of that sine wave. So here we have again the sine wave 0 to 180 to 360, one complete rotation. So when the loop is vertical inside the magnetic field, straight up and down, there is no EMF. When the loop goes this direction, so here it's flat, and then here what we have is the negative side of the current is on this side, and the positive end of the current is on this side of the loop. That leads to a positive current. Then we're going to end up back vertical again, the opposite direction, right? Here this negative side is on top, here the negative side is on the bottom. But it's vertical, so back to zero. And then as we continue to flip, and now the negative side is over here, that gives us a negative current. And then we continue to flip, we're back where we started, bam, back to zero. So the maximum current flow, either in the positive direction or the negative direction, occurs when the loop is horizontal in the magnetic field. Zero current occurs when the loop is vertical in the magnetic field. Okay? That is the key idea in terms of alternating current generators. That's what you need to know about them, all that stuff. So that's it for this video. Thanks for watching, and we'll catch you in the next one.